Alright, hello ladies and gentlemen. Today we're covering the topic of continuous functions, or differentiability of the function. They have kind of like slightly different meanings, but we'll cover the difference between continuity and differentiability and their similarities. And we know that in the previous videos we consider real value functions that have their domains of the set of natural numbers. That is, we consider the sequences of real numbers. And we now begin the study of the real value functions having as their domain a general subset of real numbers. And we know there's a standard notation of a function for a set of real numbers d. We write it as f, taking d as the input domain, to r, which is the output, which is the real value function, a real axis or real domain. And we denote this function d, whose domain is d, whose codomain is real, anything on the real axis. And we'll just say, without further mention, that d is a subset of real numbers. So in the future, when you look at d, you'll know that it's just a subset, contain a part of the real numbers. And we know two of the concepts essential to the analytic description of functions, f, are continuity and differentiability. And the first 5 sections of this chapter, namely the first 5 sections of the videos, are devoted to the study of continuity. And in the final section, we'll study the limits of preparation for the discussion of differentiability, which will begin in chapter 4 in the future. So now let's just start with the definition of continuity. What does it mean by a function being continuous at the point? So we say a function f is continuous. I'm going to just write it as CONT, abbreviating continuous at the point XO in D, provided that the following conditional statement is holding true. So what is a conditional statement? That's very important. So we know that whenever a sequence xn in D, we know that it's in D, this sequence converges to XO. Alright, it is a sequence that converges to a certain point at some fixed number on the real axis. And we know that the image sequence, which is f of xn, right? The image sequence is converging to f of xo. If this conditional statement is holding true, then we'll know that this function is continuous at xo. And what does it mean by a function to be continuous? It happens provided that it is continuous at every point in D. So if continuous at one point, but not continuous at another point, it does not mean that the function is continuous. The function is continuous, it has to be continuous at every point. Alright? So this is just a basic definition of continuity. And I'm going to give you guys some example. First of all, I would like to show you that if we define a function to be 1 and 2 at different range, at different domain, it equals to 1 when x greater or equals to 0, and it equals to 2 when x is smaller than 0. So the function is going to be, after you draw it, you'll realize that alright, y equals to f of x. So the function is not continuous at x equals to 0, because you see, first of all, just like literally when you look at it, the function is not continuous by definition, because when you approach it from a right side and left side, it looks like just very different because they are not connected. So we say that it's not continuous by intuition. And first consider it, the limit from the right side is not equals to the limit from the left side. Alright, so after we cover the definition, there are some basic theorems that are worth to be remembered. First of all, if we say that if there are two functions to be continuous at a point xo in D, we know that their sum and their multiplication and their division are all going to be continuous. So namely, if f and g, if we name them f and g to be continuous at some point xo in D, then f plus g at the same domain and same codomain, and f times g at the same domain and codomain, f over g, where g has to be not equals to 0, g not equals to 0 are all continuous at xo. Alright, so the proof is relatively easy. You can just try it on yourself by using a definition of continuity, and I'm going to just cover it in the future practice videos or somewhere, but if you're not sure how to prove it, you can always email me, and I'm going to keep going to the next theorem, which is the composition theorem. It goes hand in hand with the last theorem because it also tells you what is the whether a function is continuous or not by combining two functions. So if we have f from D to R and g from, let's say in this case, U to R, such that we know that f of D is contained in U. And now let's suppose f is continuous at xo in D, and g is continuous at f of O0, then we'll know that the composition f g o f, which is namely g of f of x, is going to be continuous at xo. Alright, so what does it mean? It means that we're given a function f, and you're going to take a certain range of domain of values. Such domain is D, right? After you take this domain, we're going to have an output, which is the codomain of the real number. Alright, this real number that we already computed as the codomain is going to be inside U, which is going to be inside the domain of G, the next function G. And this new function is going to generate a new codomain, which is the codomain of G, which is R, right? Which is again on a real axis. So this is the relationship between the two functions. So they can go together. You can input the value of the codomain of one function as the input of the other function. Alright, after you look at this relationship, and suppose that both of the functions are continuous at this given point. Notice the given point is different because their codomain are different. Their domain are different. F is taking the domain of any number in D, right? So xo is going to be a point in D, and f is continuous in this domain. Again, g is going to be continuous in a new domain. This domain is the output of f, which is at some point in U, it's going to be continuous. In other words, f of xo is going to be continuous. So if both of them are continuous at a given point, then their composition is going to be continuous at this point, which means that g of f of x is continuous at xo. As you can see as how I write it above.